Can you see my screen?
Yes, sir.
Okay, so I'll assume there are no questions. It's a short test, don't be too tense. It's kind of test your basic understanding of topics. So we'll see how you do. Don't worry about it too much. So we'll start with a new topic today. But before we do that, there's something that we discussed at the end of the last class that I want to recapitulate because it's important to have that picture in your head. A couple of you have asked me some questions also on that. So what does a LAN, basically what I want you to recapitulate, what does a LAN look like nowadays, okay? And so that's the picture that you should have in mind. And then kind of, I'll try to put in perspective all the things that we have learned in the context of where is it used out here. So first of all, there are no hubs, there are no pure shared medias as we have seen, okay? So what you have are switches, okay, with ports in there, and these switches will be connected in arbitrary topology. Okay, there may be a connection from here to here, okay, here to here, and so on, okay, and there will be other ports. So you can connect a switch with a port, or you can connect machines, devices with a port in the switch. Okay. First thing, even though the topology is arbitrary, at any point of time, the functional part of the switch, that means over the wires over which packets are actually being forwarded, will always be a tree. So for example, the tree can be this one, just as an example, okay? So these ports, these links that are connected to ports that are not part of the tree will be blocked and not used for forwarding. So they will be in a blocked state. And that is the function of that spanning tree protocol that we have kind of seen. We have not seen details that are not necessary, but it kind of elects a route and then finds the path, shortest path to those routes and so on, and selects that only that link in that path basically from every device. So that's the one thing. So you have this thing out there. The second thing we want you to know is that, so just think of a situation where you've got all these 5 switches fresh from the market and you have put it in and you have got your LAN cords and you have connected with these things, your device, some computers and so on, and you have created this topology with the switches. Okay. So as we have seen, this remains the same as what we learned in theory, that at the beginning, the switch knows nothing. There is no hard-coded table that you statically put in the table switch. Okay. So when a packet comes, switch does not know, switch will forward to everybody. But then it knows, because that frame has come, I should not use the word packet, frame has come. So from the source address field of that frame, it knows that if the frame has come from here, this port is connected to that source address. And slowly, as everyone sends a packet, this switch learning table, as we have seen, will be complete. We have seen that. So eventually, each packet will only go out around, unless it's a broadcast packet, that is the all one destination address, which will go out on all ports anyway. But otherwise, it will go out only on the port that matches in that table basically for that address. The second thing. Third thing is the inside of a switch. Okay, so you see a port. Okay, so if I just draw it vertically, okay, so what we have is you have ports out here. You have basically the basic logical architecture is this. You have a buffer with every port. Okay, these are the same ports. Okay, I've just drawn it logically. I'll explain. And then there is a middle. You have a CPU and memory, and it's just like a normal simple processor. Okay, it's just hardware. So when your packet comes, okay, it goes into the buffer. The CPU is, according to the policy, will pick things out from these buffers, look at the switching table, decide which port it goes to, and then it puts in the buffer of that, and then there's a logic which a circuit here which sends it out on that port. Okay, so in practice, for low cost switches, you won't have a per port buffer, but somebody will have this entire thing in a single RAM. So the switches will share basically, so that even if somebody is not sending, but somebody is sending at a faster rate, okay, there is enough space for that. Okay? But logically, basically your packets are first buffered, then the CPU picks it up, and then the CPU puts it out. So this port and this port are the same ports basically. Just think of there are two wires. Sorry. There are two wires which are coming in and two wires which are going out for the full duplex operation. Okay. So coming back to what we learned in theory, this means that for a switch, okay, there is for a full duplex operation in a switch, okay, there is no collision. Okay, so you'll have basically four wires sort of. Okay, the exact correction is not important. Two will be used for sending the packet, two will be used for output. Okay, so the only possibility, so your collision domain basically becomes this one link. Okay, but even there for full duplex operation, what is happening is, when can collision happen? Only if two nodes, okay, send to the same port. So that there is a device connected to this, both these nodes send here, okay, and then there are packets coming here. So ideally, kind of that both of them are trying to use, but there is no shared link anymore. So the collision domain is broken up by the switch here. Okay. So what will happen is the packets are buffered. Packets are buffered. There is no collision per se. Okay. There is no jamming signal, nothing. All right. It's just that if you are sending it too fast and there is too much load on the packet, switch, and switch is low cost, cannot process that fast enough, some packets may get dropped. Okay, but there is no collision, as we have seen. Basically, the signal level increases and so on and so forth. Basically, okay. So where does the collision come? Remember, even though I said that most switches are high-speed switches and so on, but that's only for your laptop, desktop, these devices that can generate that much traffic, lot of traffic. You watch movies in there and so on. But then that is not the only kind of network that exists in the world. You connect everything to the network, small devices, industrial devices, okay, many other things, which generates kind of very low amount of traffic sometimes, data sometimes. Okay, so you still have lower cost switches with lower rates of data, wide applications of that. So if you use half duplex, okay, because not everybody will be capable of full duplex and so on, and up to 100 Mbps you still support half duplex. 1000 Mbps is onward, gigabit onward is full duplex. So think of this one port and one device connected here. This is your device. So basically this port out here, okay, these collision domains are broken up here. Basically this port out here kind of acts as a device. So now this link is half duplex. That means if somebody is sending something through here, that is buffered here, but then if this is half duplex, this cannot send it here. If this is sending it here. So between this one and this one, if it is a half duplex operation, this is a shared media, you still have all those CSMA CDs, all those things. Okay, jamming signal, everything, but the switch is generating that, not there is no end device out there. Basically. So your collision domains are kind of broken up into this one link out here. Okay, but physically what is happening is, because the switch does not generate any traffic per se, so somebody else sending something for this node, which is buffered and the switch logic forwards it here. This is kind of acting as a device, as if it is generating the traffic. And for half duplex operation, you have a shared link out here, and you will again have CSMA serial. So for low cost devices, industrial devices, you still have 10, 100 Mbps switches and so on, 10 Mbps switches and so on, basically. And you will support that supports both half duplex and full duplex. For half duplex, you will have this shared thing out. For full duplex, again, it's nothing. Are you with me? Yes, no? Yes, no?
Yes, sir.
Yes. Yes. Point that I'm trying to make, that you will learn a lot of theory, okay, but then you need to kind of map it into a picture which says that, okay, this is what happens now, this is where this theory is coming into picture, this part of the theory is not really used much, and so on. But as I said, CSMACD is going to be important here if you have duplex operation. And there are places where you still have duplex operation. You won't see it in your normal institute LAN and so on. We have all full duplex operations. So just as an example, I'll show you something before we start the topic. So this is basically a very simple D-Link switch specification. Okay. So it's a 16 port switch, this is a 24 port switch. So you say it says 10, 100, 1000. That means to each of the switches, you can either connect a device that can operate only on 10 Mbps. Then the switch that port will operate at 10 Mbps. You can only connect a device which can operate up to 100 Mbps. Then that port communication will be 100 Mbps or 1000 Mbps. Now, all of them need not be the same. So it is possible that on two of those ports, you connect a device which can only generate 10 Mbps. But then on the two of the other ports, you connect a device that can generate 1 Gbps. So you can connect different speed devices to different ones. And that auto negotiation that I talked about will happen when you connect to the port, so that the switch will know this device is 10 Mbps and therefore I can go back to this 10 Mbps protocol out there. Okay. Now, one thing that you notice is this: all the ports are of the same capacity. I mentioned about this when you connect a switch with a switch. Okay, then this connection is carrying all the data of the first switch's ports. So this port, which is traditionally called an uplink port, okay, logically, okay, should have a slightly higher bandwidth, somewhat higher bandwidth. Okay, but then because that increases the cost also. So I could have said, and you would see that later on, I'll show you more specifications. Okay, higher end switches where two of those ports may be 10 Gbps ports. Okay, and that kind of figures, because see, if this all these 16 ports, suppose I have to connect a switch with a switch, I can only use a 1 Gbps maximum connection. I'll connect one port here with one port here. So I can only connect a 1 Gbps connection. But then there are 15 other ports out here. If they all generate traffic even at 200 Mbps, that will be a total of 3 Gbps of traffic. And then this uplink port of 1 Gbps may not be able to transfer the traffic out of the switch. Okay. But then 200 Mbps per port per device, okay, like your laptop and all, is a huge bandwidth. You never use it unless you do something very special case or something. So this is a low cost switch. You make the assumption that most of these things will connect to a normal computer, laptop, desktop, and so on, which will generate up to what, tens of Mbps, okay, 10, 20, 30, 40, 50 Mbps. So even if like 15 of them generate 50 Mbps, I have like 750 Mbps. That is still lower than 1 Gbps. So my one single connection, even if all of them generate at peak speed, which is also unlikely, my 1 Gbps connection can take it to the next switch for communication. But if you increase the hierarchy too much, remember that the higher level switch now kind of is getting more traffic. But again, 50 Mbps per device all the time is huge. It never happens for kind of end devices. And if you have applications, you will kind of buy higher cost switches where you will get, as I said, two of those ports will be 10 Gbps switch. So the switch to switch connection will be 10 Gbps. Device to switch connection will be 1 Gbps. Okay, so this says basically these are the standards coming. What are the standards we support? So these are some of the words we have seen. 10 base T, 10 base JS, 100 base C. All of them are T's, which means it can only take, all the ports will be RJ45 ports. Okay, and they can only take copper connection. Your standard LAN cables. You cannot put this. So this switch does not support fiber. Okay, see, it supports auto negotiation. Is a thing that we talked about. It does support 802.4 flow control, but as I said, if you use plain Ethernet, it will not use it. Okay, but look at the IEEE 802.3, all these things out there basically. But 802.2 is not part of the switch. This will give you something that 802.2, if you want to do, that has to be in your driver hardware. Okay. Then you have your data transfer rates. So half duplex is 10 Mbps. When we say 10 Mbps line, it's a half duplex shared media. Now, if you have both ways connection, each side can do 10 Mbps or 20 Mbps. The same thing out here. This is what I was saying. Gigabit Ethernet is always full duplex. There is no half duplex operation supported for gigabit. So it is 1000 Mbps in one direction, 1000 Mbps in other direction, so it is 2000 Mbps. Okay. It also specifies what cables it can support. Okay. So I said it's always copper, but you see that for 10 Mbps, it can also support Cat3. For 100,000 Mbps, you must have at least Cat5. You need better shielding because now it's a very simple common sense thing. As your data rate increases, your pulse size decreases. Okay, if your pulse size decreases, basically interference can affect, even for a short level interference can still, because you're kind of sensing in the middle, so even a short interference can actually has a higher chance of a bit being misdiagnosed, basically, misdetected, basically. And then you have all these other things, and these are the other thing that I want you to see. So this is the buffer I was talking about. So this is a very low end switch. So you don't specify per port buffers. Later on, I will show you a very high level, that is a IP level switch, and then you will see, this much port buffer per port. But this is like a common buffer for data buffering, basically. You have 512 kilobytes of RAM, not too high, basically. Forget about these jumping from frames and so on. But this is switching capacity. The 32 Gbps, because there are 16 ports of 1000 Gbps, and then you have full duplex operation. So when you choose a switch, okay, you will always see there's a link between switching capacity and that. The switching capacity will always be at least 2 times the maximum capacity of the ports. Basically, because maximum is maximum, everybody transmits data in that direction speed, and 2 times because it is full duplex. So 16 into 2 is 32. This is 24 into 2, 48 Gbps. These are some other features out there. I just wanted to show you very, very simple switch specification, just to make sense out of those buffers and all those things out there. Okay. Is this clear? Just wanted to have a picture of the LAN that is being used. As I said, now it is even more complex because remember the definition of LAN was if one node broadcasts, that means puts out a frame with all ones in that DA address, destination address, which all machines get it. Now in this simple, it's kind of modern day LAN, but still simplified picture that I've given you, it will go to all the ports in all the switches because the entire switches form one LAN in the picture that I've given. But now you have something called a virtual LAN, where even in this picture, I can separate out 3 different VLANs, saying port 1 and 3 in switch 1, port 7, 8, and 9 in switch 2, and port 10 and 11 in switch 3 is one LAN. So when port 1 in switch 1 sends it, a broadcast, it will only go to these ports, not to the other ports. But let us not do that, please. But just be aware of the term VLAN, virtual LAN, so you can do this, basically. Is it okay? Do you have a picture? Yes, no, please.
Yes, sir.
Okay. Good. So let's start with what we want to do today. So before we start with, we have looked at Ethernet. Now Ethernet will carry higher level protocol packets as part of its data. And the most common thing that carries is IP, so we'll study that. But before we do that, we'll see where is the IP coming, because we got everything that we have for making communication over one link. Actually, over multiple links connected by switches also, we have got everything. Okay. So a wide area network is a term that is kind of more generic. Okay. So it's a wide area network. So idea is that spans over multiple, wide area. Internet is a kind of the mother of all wide area networks. But unlike LAN, which has kind of a definition in terms of a broadcast domain and all, wide area network does not have that clear definition. How wide is wide, which are the ones, and so on. Okay. So it refers usually to networks spread over a large geographical area, connecting smaller networks, which can be multiple LANs or even sometimes combination of LANs together and then interconnection of those and so on. So as I said, when we talked about LAN, even LAN can span over a larger area nowadays. Okay. You just put an optical fiber cable and appropriate switches so that the data can go without any problem. But again, basically, that is usually you will see LANs over a smaller area, okay? Hundreds of meters and so on, like a campus. And so on. Now, if I think about a large geographical area connecting lots of these machines and so on, I know how to interconnect these local machines in my campus. But then think about all the IITs in India. They each have this local network. Just suppose for simplicity's sake, okay, that everyone has just one, just suppose. But then there are 22 IITs and so many NITs and so on. So each of them has one LAN. And now I want to interconnect them so these IITs and NITs can exchange their data. So obviously I cannot directly connect everyone with everyone. I can't form a complete graph. The number is large, that will require me too many links basically. Cost is a very, very important feature. I cannot directly connect for no other reason other than cost. Okay, almost always. Otherwise, direct would have been great. So they are large number, they are geographical far apart, so both of them drives up the cost. So connecting all of them together is not an option. The other characteristics of a WAN is that usually all machine nodes will not under the same administrative control. A LAN will typically, IIT Kharagpur LAN is under the control of IIT Kharagpur. IIT Bombay LAN is under. Again, I'm talking a very simple case where there is suppose there's only one LAN per institute. But then I cannot do something in the IIT Bombay's LAN basically because I am not the administrator of that. So how do I so the topic that we're now trying to start is, and where IP will come in, is how do I interconnect all these different networks that people have formed over which each of them has administrative control, but no one has administrative control over the entire thing. Second, there will be standardized protocols that everybody must use, put things in place, and we'll see that's what we are going to discuss. So in cases like this, transmission is done by a network of switched nodes. Okay? You have already seen switched node, okay? So nothing new. So your end devices will be that, in this case, when we talk about wide area network, the end devices will be devices that actually wants to send data. IP phone, PC, laptop, whatever, a sensor, whatever. And your communication network will be a collection of nodes and everything, okay? Now let's look at a picture. I think this will be easy. So you will have these end devices, and this cloud is going to be your network. Now for a LAN also, we have specified that cloud for a local area network, but then we have seen topology and so on. It's a small thing, so we do that. Okay. But then something in these nodes, so these are what are the, again we'll see the old days, it was always called routers, now it is routers, L3 switches and so on, we'll discuss them. So this node's functionality, they are interconnected but not necessarily completely, actually never completely, okay, for cost reasons. So they are the ones which will switch my data. So this will kind of try to decide, oh, this is sending to this, oh, I have to send to here. Then this decide, oh, this is sending to this, I have to send to here and not here. Okay. So these are the nodes which will look at your packet. And similar to what we did in the switches, but lots of different algorithms, different fields and so on, we'll try to decide basically which way to send it. So again, we'll see how it is done, but there are two key switching techniques. Circuit switching, which is not really relevant for computer networks, but you should still know the term, and packet switching, which is what we use today in all internet communication basically. Okay? So packet switching will be our focus. Or actually even something within packet switching, we'll see. So circuit switching is simple, just for completeness sake. Okay. So basically a physical circuit, okay, will be created first between the source and the destination, and then you will have everything of the communication will go over that physical circuit. So there's an established phase which says signaling up and down, somehow to form that circuit. We'll see how. Transfer, which is actual transfer, and when finally you're done, disconnect. So it's like your old days phone networks where, over the telephone exchanges, which were your switching node. Okay. relays will shut click to kind of actually connect an incoming line with an outgoing line and so on, which is kind of connecting those links in the graph. And only when the complete path is formed will the other side ring. So when you pick up, you have a physical path. Now for every subsequent data that you send, you don't need to do anything. So once you spend the time to establish the circuit, in the circuit stays, and you communicate everything over that. Okay? But you still have to find that path. So you still have to find that path, and there's a notion of routing that we'll talk about. This is a major thing that we'll discuss today. Circuit switching advantages, as I said, is simple. Once connected, transfer is fast, no forwarding deletion. Rest of the data can just go like that. Okay. Disadvantage is inefficient. Okay. It was nice for voice communication because once you pick up the phone, you keep on speaking. It's not that you pick up the phone, then you don't talk for 5 minutes, okay, and then you talk for 1 minute, then you don't talk for 2 minutes. That does not happen. Okay. So the line that was set up for you is used by you for some time, and then you disconnect. But data communication is not like that. Okay. Sometimes you will have data to send between the source and the destination. Sometimes you will not. So you'll send 100 packets. Then for sometimes you will not send anything. Okay, or let's not use the word packet yet. Let's see circuit switching. Say you will use 100 bytes of data, then you will not send anything. Then it will come back, send 2000 bytes, and so on. So if no data is transmitted, if the line is reserved for that particular source and destination, the capacity is wasted. Okay? Because you can have only so many, you can understand only so many lines dedicated. And the setup connection takes time, of course. So, as I said, it's not done in computer networks. What we do in computer network is packet switching. So, data are transmitted in short messages called packets, and a maximum packet size is defined. It's similar to what we studied in frames. You will see this notion of a data unit in every layer is just what we call it at different layers. In the data link layer, we call it frames. In the network layer, which we are starting now, is what we call packets. Okay. And you don't mention a dedicated connection between the two end nodes. So if I now have to send, let's say 50,000 bytes, and my maximum size of a packet is 2000 bytes, I'll break up the 50,000 into 25 such 2000 byte packets. Okay. Then I will put some header information along with it. This is the cost that I'm paying over circuit switching. I add some overhead. Okay. And then these intermediate nodes, okay, which is the routers, we'll look at that header. They say, oh, the header is okay. So this packet is destined for that destination. Do some magic, okay, and send it to the appropriate direction properly. It's called a store and forward for the kind of thing that I just showed you at the beginning of class. The packets will come into the router. They will get stored for temporarily. Then the router CPU will process it, decide out of the router's ports which outgoing port it will go to, okay, and put in the buffer there, which will be sent out there. So it will store and forward the packet towards its destination. So a router's logical picture will be very similar to what I've drawn for a layer 2 switch. The packets will come in, we're not talking about packets instead of frames. The packets will come in, the router will look at the frame, the packet header, based on some things in the packet header, which we'll study. It'll decide out of the 4 links going out of the router, where should it go? Okay. So the router interconnection is basically a graph. So it gets this packet from here, it decides out of these 4 other links, okay, the destination maybe go towards this. How does it find that? We'll talk about that. Okay. But it looks up a table similar to that switching table that we have seen. So this destination, this one, send it out of this. Then this one will do the same thing. This destination, this one, send it out this thing. Finally, when it goes to the destination knows the destination. Nothing further needs to be done. Okay. And the advantage obviously is that node to node link, that means between 2 routers, let's say, can be shared by multiple packets. Okay. It's not dedicated for anyone, so it can at any point of time take, so I can have in the link, I can have 5 packets transmitted which are still on the link. This is from one source destination, this from another source destination, this from another source destination. Okay. So if this is not sending, this link can still be used by this and other source destination pairs. It's kind of easy to understand. And this is just logically a picture of what I just said. So you have your application data, break it up into packets, put a header with each of them, send it. Packet switching network does not look at the data. It does not care whether it's a movie or a text file or this or that. It looks at the header. You will study this header in detail. This goes in. On the other side, you again kind of put them, take out the headers, put them in the appropriate places in the total application data, and then give the application data to the user. But you already see there are things coming in. So at the thing here, it needs to know which part of this, which packet to be put in which part of which here. If I put this one in the first part, this one in the last part, my app data is garbage. Okay. So you already start seeing small issues. We'll see how we solve them. Now within packet switching also, there are two approaches. Okay. One is called a datagram approach, where each packet is treated independently. Okay. I look at the header, and then packets may follow different paths to the destination. So even if I have source 1 to source 10, it is not necessary that all packets of source 1 to source 10 will follow the same path. Okay. So this has the advantage that suppose source 1 is sending to source 10 here, okay, and there are two paths out here. When it sent the first 10 packets, this side was not crowded, so this all went through here. When it sent the next packets, maybe because other people were sending here, this link got very crowded. Okay, so this will be detected. Don't worry how it will be detected and so on. Okay, and it is possible in datagram approach that the next packets can go here because this link nobody is using. Nobody is sending packets to these routers. Okay, so upshot is that the packets can travel different paths to different distance. Okay, what is the problem? If I allow this to happen, something core I've told you in the first class. Okay, it's all about asking questions and designing things, understanding the problems and so on. Otherwise, you will just mug some information. You'll forget it in 1 month or even less than that. And for that information, I don't need to teach. I can just point out resources, you can study and you can get them. So what if I allow this to do, that means for the same source destination pair, think of that I'm sending a file. I've broken it up into small packets. I'm sending the files. Okay. And then I allow this datagram approach to happen. Why is that? What problems can it cause? Any guess? Can you hear me?
Yes, sir.
Yes. The answer is here. Okay, so that means, see, think of this as a file. Okay, you want the first, if you send this, okay, on a one link, even though that also may not happen, okay, but on one link, okay, you can still say, oh, I've sent this before this, so this cannot jump over this, so everything goes fine. Then this will be received first by the destination, then this, and so on. Okay, but when you put on two links, there will be different delays and all. So it is possible this were your 1, 2, 3, and this were your 4 and 5. Okay, in order, and then this, because this link was become crowded, that's why I'm using this link. 4 and 5 reach earlier than this. So then you cannot give the 5 because 1, 2, 3 has not arrived. Okay. Now you can discard. You can go to that go back in and all those things. But see, go back in and all is extremely costly over this entire big network. Because whereas in a LAN, okay, it's just over one link. So you just send it to that party and that party sends it. The propagation delay, everything is small. Okay, it's now going to be probably 7 routers in between, 5 routers in between. Some of them may be very busy also. Okay, so now your scope of who is using the network has increased. That means the load on the network is increased. That means if you do go back in and simply reject 4 and 5, okay, it's going to be a problem. So you will need to buffer at the receiver, wait for 1, 2, 3, there must be sufficient buffer, recover the missing point, reform everything together in order and so on. So all these things we are kind of stating requirements, what problems can happen and what do I need to have. We are not talking at all anything about how does it happen. That will see. Okay. Okay. But you see again there is a router. I still need to find for each packet also I need to decide if there are 2 links out here that this is the link it should take and not this one. So there is a notion of routing that comes in. So this is just same thing that I have drawn. Okay, it's just an example that we have 1, 2, 3 and then 3 follows one path, 1 and 2 follows the other path. Okay. Just an example of that. You can do it yourself. As opposed to that, there's something called a virtual circuit. So similar to circuit switching, it first have an call establishment kind of phase, okay, to establish the route. So similar to circuit switching, for a single source and destination, it will have it route, fixed path. But unlike circuit switching, that fixed path will not be dedicated to the source and destination. Others can also use or parts of the path. Okay. So if I have something like this, okay, and I have my destination here and my source here, okay, I can decide that this is the path I will follow based on something. I will decide that a priori, and then every packet for that source and destination I will send along this path. So that the per packet thing that had to happen for packet switching, that processing which will delay things little bit at every router, that delay is reduced. Okay. I spend the similar to Kong, I spend the connection establishment time. Okay. But then that while I send the packet, the delay is reduced and everything goes in this thing. So unless other bad things happen, they will come in order. Okay. Other bad things like one packet may get corrupted. So you may still have like a missing packet in the middle. May not be out of order, but a missing packet. Okay. But then, unlike circuit switching, it is also possible that there is another source S dash, okay, which wants to communicate with D dash here, and the datagram approach, this also forms a path like this. So this link, and this link are shared between the two datagrams. So even if this is not using, this can still use it basically. The problem that we had about circuit switching, that I dedicated that for S to D, saying those links cannot be used by anybody else. So S to S dash to D dash path could not have been established. Okay. So to summarize, we have packet switching, circuit switching and packet switching. Circuit switching not used in computer networks. Packet switching, we have datagram and virtual circuit. Okay. Understand the pros and cons, what they are. Okay. What we will do is packet switching datagram. There are some protocols that use virtual circuits, but bulk of the thing that we see and that we study, we'll talk about packet switching datagram. That means no path established at the beginning. Every packet will have some header information. Router will treat every packet independently. It looks at one packet, based on its header field, decides where it should go out of its different ports out there. Okay. So these are just pros and cons that I've already discussed. You can study them later on. Okay. But here is a thing that is a picture that you should kind of remember. Okay. This is a trade-off. So this X, A, B, C, these are links. So there are 4 nodes. This is the path X to A to B, B to Y. Okay. And this is the time. So kind of think who is doing what out here. So if I have larger packet size, okay, the header size is kind of fixed always. We'll see. Okay. Larger packet size. So this is the node A. So node A cannot start forwarding the packet until it receives the entire packet. Okay. But then only it will look at the header, it will do some error checking and so on. If the frame is proper, only then can see. So the time that you take is this one, because for each of the nodes B and so on, so X to Y communication cannot forward the packet, the intermediate nodes, until it receives this. As I reduce the packet size, okay, what is happening is now node A does not have to wait for the entire data to come, because it has received one packet, it's independently going to forward this one packet to the A to B link. So this is the packet data one has gone on the A to B link already. While X to A link is still carrying the second packet of the, or the second sub packet, so to say, of the first packet here. Okay. If you increase the packet size, the time goes down. But see, beyond a certain portion, the time kind of increases. So think that, when I kind of did half, the packets, my transmission time, total time to transmit the Y to receive the frame, Y to receive the entire data from X went down. Then the slope becomes smaller and then eventually become higher. Because now you just see the gray parts are increasing like anything. Okay. So ultimately it will depend on the total number, the time will depend on the total number of bits transmitted. But now slowly as you break it into smaller and smaller packets, you are putting a header with each packet. Okay. So the amount of non-data bits, your overhead bits are kind of increasing a lot. And they are kind of adding up to your time of transmission. So eventually as they increase more and more, okay, this curve will fall down and you will actually take more and more time. So deciding on, I would not use the word optimum, good packet size is very important. And as I've said at the beginning, it's going to be full of design questions. Slowly see more of them. And there are no hard and fast great answer to that. Okay. So if your link is very fast, you don't really care. You can actually have smaller packet sizes. Okay. But you have long fast links, then your packet size would, if you're sending more non-beta dates, okay, you take more time to recover from this, sort of. So this is what I'm pointing out. If you mug the protocol, you can say, oh, maximum packet size out here is this. I would like you to ask basically why is this? What would have happened if this is more than that? Now this why question sometimes for old protocols is hard to find. But then again, you can start thinking at least, what could have prompted me to choose, say, the maximum packet size is 1500. It's just a number. And there is usually no concrete thing why it should not be 1450 or 1550, nothing like that. But always ask questions actually like, rather than just saying the packet size, what would determine my packet size? You will see it in OS also, there's full of such design questions out there. Okay. So that's about packet switching. So the summary is that from what now we'll study is basically packet switched networks using datagram approach. Okay, that's what we'll study from now on. But then in all of these things, whether you do circuit switching, this and so on, okay, there's a notion of a route. Whether you do it a priori or per packet or something, each of those routers has to determine, okay, out of my 4 outgoing links, which is the one that I'm going to send this packet to so that it reaches the destination. So that is the primary function of network layers, as we have seen, to form routing tables, sort of, to decide on routing. So routers, basically a network layer protocol will say that when I get the packet, okay, how do I forward it? Which will call the question, how do I find a route in this thing? So it's nothing but like think about a graph, okay, finding a proper path in the graph. Now, only problem is that this graph may be very large. Think about the internet. So you cannot apply your standard Dijkstra's and this and so on the internet scale graph because you first of all do not know the graph. How will you know the graph? Everybody will have to tell you. There's nobody single one to tell you. And it keeps on changing. Link keeps on going down, going up, and so on and so forth. Okay? So routing is a very, very important critical issue in internet. Okay? So when you have a large network but the entire thing is not known to you, okay, how do you route? but we'll see what happens out there. So I'll just do this one and we'll stop here. We'll start again after the exam tomorrow. I'll just use the notion of a routing table. So what is routing? It's the process of finding a path from a source to destination through intermediate nodes. So these are basically my routers. Okay. This terminology route is a path from the source to a destination. Router is this intermediate nodes that forward the packets. Okay. And what will happen is in every machine on the net, including your laptop, desktop, and so on, there will be something called a routing table. I'll show you the routing table on my machine, for example, when we study this. Okay. Maybe tomorrow or maybe in the next class after that. So it's kept at each node that wants to communicate in the net. Okay. Logically, you'll see that what is contains the route to each destination node reachable from that node. So if I have a graph, okay, and if I think of these are like A, B, C, D, E, F, G, okay, and if I look at B's node, you'll have an entry for A, entry for C, entry for D, okay, entry for E, entry for F. Entry for G. Okay. But if there was another, somehow the node network is disconnected and it has 3 nodes, you don't have entries for them eventually. So there is a protocol that will run in the background. Okay, because see, initially if I just like my switching table, okay, if I buy a fresh router and put it out there, there is nothing out there. But routers will see that we can do different things. Some of them we can add manually. Okay, in a switch we never almost add manual things. We can. Okay, all switches give, most switches give you that facility, but you normally don't. The switch learns basically in the standard model that we have seen. Okay, but in this we can add statically if we want. But then for large network, that is not a desirable option. It's only for very small things you do that. So there will be a protocol running in the background. It's called a routing protocol, whose job is to kind of do some magic with this network and fill up the routing table. So for each of them, it will have basically something. We'll see what that something is. So when a packet comes, this router will just look up and say, oh, the destination is G. I'll go to the G's entry and I will, based on here, I'll decide what to do out here. Okay. Something else happened. Anyway, we are at the end of the class anyway, so let us not worry about it. Okay. So with this notion of the routing table, that is one entry per destination reachable from the node, we end the class here. We'll start it tomorrow after the exam to see what goes into these things, and then we'll start looking at routing protocols to fill up this routing table. Okay. So we stop here. If you have any questions, ask me. Otherwise, class is over and you can leave.